Hello, my name's Camilla Gilmore and I'm a Professor for Mathematical Cognition at Loughborough University. And in this video, I'm going to be thinking about research on executive function skills and how they might be relevant for when we think about children's mathematical learning and thinking in the classroom. And this is the first of two videos, and in this one, I'll be focusing on inhibition. So in the video, I'll start off just introducing what executive function skills are, and then focus in on inhibition, so thinking about different types of inhibition and different types of distracting information that we might see in mathematics activities, and then thinking about what this might mean for the classroom and why it might be relevant for teachers to be aware of this. So first of all, what are executive function skills? So they're the set of skills that we use to monitor and control our thoughts and actions. They allow us to respond flexibly to our environment, and they allow us to engage in deliberate, goal-directed thought and action. And we use our executive function skills all the time. They're particularly important when learning, but actually whenever we do any activity where we're having to being intentional about what we're doing, and we're having to deal with information that we're taking in from the environment that we're seeing or that we're hearing, we're always going to be using our executive function skills. And there's a number of different theories or models of what executive function skills are and how they're made up. But one of the most commonly used is this proposal from Miyake and colleagues that we can think about executive function skills as having three different components. So this includes working memory, inhibition and shifting. So working memory is involved whenever we have to hold and manipulate information in mind. So we have a limited capacity for the amount of information we can process and hold in mind for short periods of time. And shifting skills, or sometimes called cognitive flexibility, this is involved whenever we have to switch between tasks, particularly if we're switching between tasks in the face of some interference. And also they're involved whenever we're looking at different perspectives on a particular situation. And inhibition is the one that I'm going to focus on today, so I'll explain what that is in a moment. I think it is important to point out that while this idea of executive function skills having these three separate components is well evidenced, it's also the case that when we look at evidence from children early in childhood, we often see that we can't really distinguish between these different components very well. And actually, when looking at young children up to about mid-childhood, that actually it might be better to think about holistic executive function skills rather than trying to separate these very cleanly into the different components. But for today, I'm going to focus on inhibition skills because from mid-childhood onwards, we can see that these are a distinct set of skills. So inhibition, or sometimes this is referred to as inhibitory control, we use inhibition whenever we have to ignore distracting information or we have to suppress unwanted responses. And I'll unpick both of these a bit more in a moment. So at a very broad level, the research suggests that individual differences in inhibition skills are associated with individual differences in mathematics achievement. But despite there being this correlation, this association between them, it doesn't appear that there's a very simple, straightforward causal relationship here, and we can't simply train inhibition skills and see a consequent improvement in mathematics. So that's the kind of high-level message, and I'll provide some evidence about both of these points in the rest of the video. So first of all, thinking about the role of inhibition to help us ignore distracting information. So distracting information can come from a number of different sources. So one of these is that distracting information can come from our environment. So if we think about a classroom situation, it can be a very busy environment. There's a lot going on, there's a lot of different people behaving in different ways. They're often quite busy visual environments as well. And so if children struggle to ignore the distractions around them, then it's not surprising that this is going to interfere with their learning. And they need to use their inhibition skills, their inhibitory control, in order to ignore these distractions that are going on and to focus on the task that they're meant to be doing or to focus on what the teacher is saying. And so when we think about this demand from the environment and the need for inhibition, it's interesting to see how children's inhibition skills develop. And there's quite a lot of evidence that shows that children's inhibition skills develop quite substantially throughout childhood. So this is data from a large-scale study that looked at children's inhibition skills on a set of standard inhibition tasks between the ages of 3 years and 15 years. And so you can see here from the graph that there's really quite substantial improvement in their inhibition skills over between these two ages. It's important to point out that this is average development and that there are actually wide individual differences. So at each age, there will be quite a range of inhibition skills. But nevertheless, the development in this average performance is really quite striking. And there's a few things I wanted to draw your attention to in this graph. So one is to see here that even at 15 years old, young people's inhibition skills are still developing. We haven't yet reached a plateau here, and we know that executive function skills in general and inhibition in particular continues to develop throughout adolescence and even into the early 20s. So failure or a lack of inhibition and a lack of ability to ignore distractions can be a result of still developing inhibition skills all the way through secondary school. It's not just something that we have to consider with young children. However, I do think it's some of the most striking data in this graph comes from early childhood, and particularly this really rapid development and huge difference in inhibition skills between the ages of 3 and 5 years old, and actually even more so between the ages of 4 and 5. So young children really have a very significant development in their inhibitory control. And looking at that difference between the 4-year-olds and the 5-year-olds made me think about the difference between autumn-born and summer-born reception children. So a child who is only just 4 could have substantially different level of inhibition control and the ability to ignore distracting information than a child who's perhaps coming up to their 5th birthday. And so we need to bear that in mind when we think about the appropriateness of our expectations and the activities that we're asking of the youngest children in school. So one place that the distracting information can come from is the environment, but another place is from the activities or the tasks that we're doing. So sometimes we have to ignore distracting information from within the task that we're doing. So I'll give you a couple of examples of that. So one example comes from sort of classic word problem. This is not a very exciting word problem, but just as an example. So if we say that John had some books, he was given 3 more, and at the end he had 8, how many did he have to start with? Well, where's the distracting information here? Well, I would suggest that the word more here could be seen as being distracting information, particularly if children have built up an association or an idea that more means add, and so therefore I'm going to add the numbers. And actually, to answer this question properly, they need to ignore this word more, or at least ignore the simple association it has with add, and think about the situation more carefully. Another example comes from this question that was from the SATS paper recently. And in this question, children were asked to identify the coordinates of the point P, and they're given some information here in the problem. And I would suggest that this number 8 here could be seen as being distracting information, because actually children don't need this in order to work out the coordinates of point P. And if they focus on this number and they try and use this actually might send them off in the wrong direction in terms of thinking about the strategies they're going to use. And particularly in a problem like this, where there's not a lot of information given to children, it requires quite a level of inhibition to be able to ignore some of the information that you've been given and to identify that that's not relevant and that you need to focus on other parts of the problem. It's worth pointing out that we don't have to consciously or explicitly think that this information is distracting in order for it to influence our responses. So we can be influenced by something, by distracting information, without consciously thinking, for example, without consciously thinking that more means add, but we can still be influenced by this distracting information. So the third place that distracting information can come from is from our own prior knowledge. And this is one that, as a psychologist, I think is the most fascinating. So let me explain what I mean by this. I'll use the example first about number fact knowledge. So when children are learning number facts, so their number bonds or their multiplication tables, for example, this information isn't stored as a list of simple facts, but actually is stored, or at least researchers believe that this is stored as a network of associations. So, for example, if children learn that 3 add 5 equals 8, then they might build up the association between 3 and 5 and 8. And then a little while later, a child might then go on to learn their times tables. And then they build up a new association here between 3 and 5 and 15. And of course, each of those numbers will have different associations. So a child will also have an association between 3 and 4 and 12. And what this means is that when we're trying to retrieve the answer to a fact that we might already know, we might have in our network of associations, we have to actually inhibit the irrelevant associations associated with that number. So if we want a child to recall the answer to 3 times 5, then they've got to inhibit these associations between 3 and 8 and between 3 and 12. And you can imagine that this network becomes very complex. The more number bonds and the more multiplication facts that a child knows, that they're going to have a very complex network of associations here. And they're going to need to use their inhibition skill in order to inhibit these irrelevant associations when they're trying to recall a particular fact. And sometimes a child may recall the wrong answer or struggle to recall an answer, not because they don't know it, because it's not in their network of associations, but actually because they've failed to inhibit a different answer or a different association. And this is why we can sometimes see children who may seem to be very secure in their addition facts, but then when they go on to learn their multiplication facts, seem to kind of lose these addition facts because they have this interference between them. And also why when children are learning their multiplication facts, we often see interference and children recalling the wrong association when they're trying to recall a particular answer, or getting confused between the different number facts that they've learnt. So another example of where distracting information can come from our own prior knowledge comes from thinking about learning rational numbers. So when children go on to learn about fractions and decimals. And an error that we often see is that children apply their whole number knowledge to the situation involving fractions or decimals. So they might think that, well, 8 is bigger than 4, and so 2 over 8 is going to be bigger than 2 quarters. Or similarly, they might have built up an idea that with whole numbers, that longer numbers are larger, and so a longer decimal might be larger than a shorter decimal. And these are both examples of what we call in research the natural number bias, or it's sometimes referred to as the whole number bias. And this is where our knowledge of whole numbers interferes with going on to learn about rational numbers. And this gives me an excuse to share one of my favourite examples of the natural number bias in the wild, here from last year, where there was a failure of inhibiting whole number knowledge in terms of thinking about COVID rates. So both these examples of the natural number bias is actually an example of the theory of conceptual change. And the theory of conceptual change suggests that our earlier conceptions or our earlier understandings are not replaced by new knowledge and understanding, but actually we keep them all. And what we have to do is actively inhibit these earlier conceptions when we want to apply new knowledge. And that importantly, this requires cognitive effort. So applying our inhibitory control to inhibit our earlier understanding is quite effortful. And importantly, sometimes we fail to apply that inhibitory control. So sometimes we don't have enough resources to apply this inhibitory control. And then we may fail to inhibit these intuitive understandings or these unwanted associations, and they can interfere with what we're trying to do. And one consequence of that is that learners can sometimes act in unpredictable ways, especially when they might be under pressure. So what do I mean under pressure? Well, that can happen in a lot of different situations. It might simply because we put them on under time pressure, or they might be anxious in a particular situation if they have maths anxiety, for example, or anyone in a test situation might become anxious, or even when they're tired. So we know that when individuals are tired, it's harder to apply their inhibitory control. We lose our inhibitions a bit when we're tired. And so because of these this additional pressure in different situations, we might see individuals failing to apply their inhibitory control. So, for example, if a child might know their number facts, their multiplication facts, but under time pressure, they might not be able to apply the inhibitory control in order to focus on the associations that are relevant, and ignore the associations that are distracting. And so they might not be able to recall the answer under a time pressure that they could do without that time pressure. Or similarly, we might see children making errors in a test situation that we would never expect them to make normally. And it's this extra pressure that means they don't have as much cognitive effort as normal, and they can't apply their inhibitory control as they normally would be able to do so. Okay, so that's focusing on the role of inhibition to ignore distracting information. But I also said that we need inhibition when we want to suppress unwanted responses. So what might make a response unwanted? Well, it could be just because it's driven by distracting information, as in the examples I've given you. But it also might be because it's what we call a prepotent response in a given situation. And a prepotent response is a dominant or default response or action that might often be appropriate, but not always. So sometimes we have to suppress, or we have to not carry out an action or a particular response that in other situations would be appropriate. So let me give you some examples of that. So if we think again about the word problem example, so I showed you earlier a word problem where we might want to resist a particular response. And if we'd before that done some other examples where actually we were reinforcing this association between the word more and needing to add, then it would be more difficult to inhibit this after a whole sequence of these examples than if we just gave that final word problem on its own. A similar example, that if we were practicing a particular strategy, for example, we gave children a sequence of problems where we're asking them to practice the same strategy, and then a problem where actually perhaps that's not the most appropriate strategy to use, and we might prefer them to think about the problem and think about different ways of solving it. If we've reinforced a particular response, we've made using column subtraction to be the prepotent response in this situation, then it would be more difficult to resist the temptation to do that, to resist the urge to do that, and to use our inhibitory control to stop and think about alternative strategies. And essentially, overall, the more established a response or action is, then the harder it is to interrupt this, and the more inhibitory control we would need. And this is often used in games and things that we can think about Simon Says as being a really good example, where the more we reinforce the prepotent action to copy whatever the instruction is, then the harder it will be to resist it when it's no longer the appropriate thing to do. So a summary so far. So I've said that inhibition is needed when we have to ignore distracting information, and that distracting information can come either from our environment or the activities or tasks that we're doing, or our own prior knowledge. And inhibition is also needed when we want to suppress unwanted responses, and especially these default actions that might have been reinforced. So what does this mean for the classroom? What are our options in terms of using this research evidence and thinking about our practice in the classroom? Well, there's a number of different options that I'll consider in turn. So one option is the idea that, well, given that there's this really strong association, why don't we just improve children's inhibitory control and then we'll see an improvement in their mathematics? And unfortunately, this is not the simple option that it seems to be. So a number of research studies have tried to train inhibition skills, and these suggest that it's not easily trainable. So some studies find no improvement in inhibitory control. Some do find small improvements in the inhibitory control training activities. But regardless of this, what we see is that the effects don't seem to transfer. So if we just do some standalone inhibition training, it doesn't seem to lead to any improvement on academic achievement. I note that, however, despite the research suggesting this, you can still find companies that are willing to sell you inhibition training, suggesting that it's a good solution. However, it's not the end of the story in terms of training. So another alternative, rather than thinking about standalone inhibition training, is thinking about how we might embed inhibitory control activities within a certain kind of mathematical activities, or we might particularly help children to identify the need for inhibitory control. And research on this is ongoing, and so this might be a more promising avenue to go down rather than just the simple inhibition training. And there's a couple of studies. So there's an ongoing EEF study that's looking particularly at trying to help children identify the need for inhibitory control and to stop and think when they're dealing with counterintuitive concepts in science or maths. And another ongoing project at Oxford University that's looking at how we can embed inhibitory control and executive function activities within mathematics activities in the early years. So there might be a more promising story to come on that. But in the interim, before we know whether that we can actually train inhibition skills, another alternative might be that, well, given that we know that inhibitory control can cause problems and can interfere with children's mathematical achievement, perhaps what we need to do is we need to adapt our tasks to reduce the need for inhibitory control as much as possible. So what might that look like? Well, that might look like lots of routine practice on very predictable tasks where there's no distracting information and children are not having to suppress particular responses and they're just having to carry out the same predictable strategy or routine. Well, if we did that, we could see an increase in scores on mathematics tasks. So if we stripped out all of the inhibitory control demands, we might see children get higher scores. But I would suggest that we wouldn't actually be improving children's mathematical thinking or understanding at all. And in fact, it could be that this leads to worse performance when children are confronted with a situation where they do need to apply their inhibitory control. And actually, we might be better off thinking that rather than being something that interferes with mathematical thinking, that actually being mathematical involves harnessing these skills and dealing with this interference and applying these executive function skills to mathematical situations. So if we strip out all the inhibitory control demands, we might actually be stripping out a lot of the mathematics itself. So I'm sort of left with a third option where what we might want to do is help teachers to have an awareness of inhibitory control demands and to think more explicitly about the inhibitory control demands of the activities that they're doing. So one part of this would be a recognition that children's inhibitory control is still developing, particularly in the early years, but actually throughout childhood and adolescence. And it might be that sometimes we want to deliberately reduce the inhibitory control demands of our activities, and at other times we might want to deliberately increase those demands. So we might want to reduce them if we want to focus children's attention on one idea or one procedure or strategy that they're learning, and that we actually want them to have the chance to practice this without any interfering information. But at other times, we might want to deliberately increase them. For example, we might want to add extra challenge to our mathematical activities, particularly for some children who we might want to be stretching them. And one way of doing this might be to increase the inhibitory control demand. So add more interfering information, make it the problem distracting, and actually see whether children can still apply their understanding in that situation. Another thing to think about is giving children time and opportunity to consider and discuss alternative strategies. So if we know that one challenge of inhibitory control is stopping to actually just carry out the same strategy every time, well, we need to give children practice in the approach of thinking about different strategies and making a deliberate choice between which strategy they do. And this is something that we might want to model and practice in the classroom. And the final thing to think about is considering how the material or ideas that we're teaching now might need to be inhibited in the future. So are we setting up unhelpful associations that will be something that children later need to use more inhibitory control in order to ignore and to overcome? So an example of that might be thinking about, we wouldn't want to build up these sorts of associations between particular keywords for addition or subtraction, because in some situations that will be an unhelpful association that children then have to inhibit. And so we need to be careful of thinking about the way that we introduce ideas and think about what's coming later in a child's mathematical learning. Okay, so just to summarise what I've covered in this. Well, I think executive function demands are integral to mathematical thinking, and that actually being mathematical involves harnessing these skills and applying them to mathematical situations. So we shouldn't think about them as something that gets in the way of mathematical thinking, but actually they're a part of it. However, we might want to sometimes be deliberate about the inhibition demands of activities, and certainly we wouldn't want to unnecessarily distract children. Rather, we want to be deliberate about the way that we include distracting information, and at times when it might be helpful to children to practice ignoring that. And finally, we need to consider the developmental appropriateness of what we ask of the youngest children who might have very limited inhibition skills. But also remember that there's variability at every age in children's inhibition skills. So thank you, and there will be a second video that will be focusing on working memory and the relevance of that for the classroom.